Okay. So I think at the beginning, Pavana is one of my best students in my cybersecurity course, right? So after that, I encouraged Pavana to join my group, and hopefully Pavana didn't feel, very bad to join my group. And during the 5-year study, Pavana did many things. At the beginning, probably mainly wireless. Later is privacy preserving stuff, differential privacy. Privacy preserving learning will be reflected partially in today's defense. I think during the last 2 years, Pamela mainly working on the fair learning, like the title show, some like mobile device friendly fair learning, work on the quantization, efficiency, energy efficiency, delay efficiency, also personalized fair learning. Also based on the previous knowledge on DP, Pamela also work on the privacy preserving fair learning, right? So hopefully I'm too drunk. Hopefully I didn't miss anything. So, okay. So the stage is yours, Pavana, please.
Okay. Thank you, Dr. Van. Thank you so much for the introduction. And thank you, Dr. Van and Dr. Han, for making it for today's dissertation. And both my other committee members, Dr. Fu and Dr. Guo, I think they could not make it right now. So I will share the recording with them very soon, so I can answer their questions at a later point of time. So I will just begin my defense today. Please feel free to ask me any questions that you may have. So welcome all. My dissertation is titled Towards Mobile Device Friendly Federated Learning, Efficiency, Privacy, and Personalization. This is a work that has gone spanned across the past 3 years mainly, and also a little bit of the background was done in my first 2 years of my PhD. And thank you all the committee members for being here today, and also for giving all your insights previously during my proposal and also earlier to that, and also during my qualifying exam. So thank you for being there with my journey from the beginning. So starting off, here is a brief outline of my today's talk. This is the agenda. I'll first talk about some background, motivation, and introduction to my work. Then I'll talk about 3 of my primary works. One is mainly the energy efficiency knowledge transfer. Then I'll talk about one of my privacy preserving papers. Then I'll talk about one of the efficiency related papers, which talks about model compression, quantization, pruning, etc. After that, I'll talk about one of my ongoing works and one of my future works. So starting off, today, we know that we live in an AI-powered world. Artificial intelligence is literally everywhere around us, from online shopping to banking to probably house price prediction, or you want to know anything about your mobile phones, any of the statistics that is being sent up to your companies, anything that we have around today, all the applications that we have from the time we wake up in the morning until we sleep, we have AI being touched with us in so many ways. And one of the more recently, something that took the world by storm is the ChatGPT. As we know, that was introduced by OpenAI. We know everybody who has any background in artificial intelligence or machine learning, who don't have any of that, people belonging to any age group, are being able to use AI today freely, mainly through generative AI methods like ChatGPT. One such example here is one of the students is taking ChatGPT's help to do their homework, to write a small snippet in Python. And maybe one of the other ones where there's a culinary industry probably is changing in the way that one of the chefs is asking how you can get an easy recipe for one of the soups, and also asking for the translation in Japanese. And you see all of these in the tip of your fingers will be available in the scope of a few seconds itself. And here are the examples. The reason why we're talking so much about ChatGPT, especially in today's presentation, is mainly because of the amount of time it took for the number of users to be available online, to be using an application that is backed by AI in the world. So for example, Netflix or Kickstarter, A&B, and all these big players, though they were launched much earlier, they took at least about 3.5 or 2.5 years to reach at least 1 million downloads, 1 million users. Whereas ChatGPT, it literally took just 5 minutes, in fact, 5 nights, and there were 1 million backers already supporting it, and 1 million downloads, and 1 million nights already booked with it. So ChatGPT became this important because of certain reasons that I'll talk about that probably made this happen. So for that, let me go back a little to the introduction about, let's take any ordinary system that we have today. And what happens when you put in artificial intelligence is AI is nothing but the human's ability. I mean, it's like human-like ability that you're building in a computer. And machine learning is a subset of AI, where instead of you writing a code and giving instructions to a machine saying that, hey, you know what, you do this, if you take this input, this is the output, instead of you force feeding something to a machine, instead you will give it data and give it the ability in order for it to make decisions eventually. So the machine is going to learn. So you're building some intelligence into the system like that. Now, one of the subsets of this machine learning is nothing but the deep learning. Deep learning, as you can see in the picture, is probably like human brain like. This was created in such a way that this machine will start imitating or emulating the human brain, where you have neurons, which is similar to what the deep neural networks have. And all the connections that go, all the synapses that go between the brain cells brain nodes will act like your connections here in deep neural networks. And these deep neural networks act as the backbone of the whole deep learning application, and all the code that you write into it will be built into this. So you can give an input and make sure that it just its own kind of learning up through several iterations, and you have the output that you want. And these things, along with all the advances that we have in processing on devices these days, you have very strong chipsets, which are advanced processors, you have accelerators, you have so many processing advancements that have happened that can go into smaller devices. And also all the advances that we have in wireless technology today, for example, the 5G or 6G, or you have the Wi-Fi connection. So all of this at the tip of your mobile phone. All you can do is just get any of your mobile devices, be it laptop or probably your smartwatch, tablets, tablet computers, etc. All these are probably fitted with advanced processing and advanced wireless capabilities, because of which you would be able to connect to the internet much easily. And because of all these backing, which comes back on the processors, you can be able to use AI applications with these. Well, this is the introduction. I'll talk about federated learning, which is a subset of this whole machine learning concept. So federated learning basically started off with a very small application of distributed machine learning, where there was a keyboard prediction. You have the Gboard by Google, where you will probably type a text message and the next word is already predicted for you. Instead of you typing it all over, the machine is going to help you predict some word based on the kind of words that you use, based on the kind of language that you use, something that's kind of personalized to the way you write text messages. You can merely literally just pick one of those words and put it up here. And this is how the keyboard prediction works. So when federated learning started off this small, today it has taken over the world much differently. For example, how Apple extensively uses federated learning, because you can use Siri, you personalize Siri according to your requirements without really hovering up your data. So because of that, you have metaverse. So you can literally learn any virtual entities using metaverse, or virtual commerce can be powered by this. Or you can have smart healthcare, where many of the healthcare institutions can come together without sharing the raw data and still be able to make some kind of predictions. Or self-driving cars, where you have some real-time information giving fed to you. There's some collective diverse driving scenarios that can be fed to the machine, which will help it make intelligent decisions very quickly. And also you have the smart industry. So instead of you manually intervening to do any kind of control, all kind of quality control and applications can be controlled and can be backed by using federated learning. Also, the most recent one is the VR surgical simulator, where it is actually much easier for medical students or probably junior doctors. Instead of doing the surgery by hand, they can use some kind of a VR surgical simulator to learn the way your organs are inside and how you can be able to do things onto it. And also any kind of advancements that probably are happening with the surgical industry or with kind of any medical industry, all those data can be updated, and it is much easier to learn it virtually and then probably do it in real time on a patient actually. So all these things are all backed by federated learning today. So what makes it federated learning so popular? Though it was just introduced very recently, in probably 2017, how did it become this popular this quickly? For that, let's take a little background on what federated learning is. So federated learning basically is driven by the motto that you learn from everyone, but without really learning particularly about anyone. So let's say you have a number of mobile devices. This can be IoT devices, or this can be any other participants like hospitals or industries, etc. Any of those. Here, I'm taking an example of a much smaller scenario where I have mobile devices. So all these mobile devices have local private data sets of their own, which they do not want to be shared outside, either with each other or with another third party. So they want it to be locked. So what we do is we kind of enable local training on these devices using their own data sets, using which you can create some local models which are specific to that particular device itself. But all these devices want to have much higher capabilities than just what they have. So what we do is we kind of do some repeated training and get more accurate local models. And we use some kind of a parameter server, which can be an edge server, or it can be another peer who can do some kind of aggregation. We consider them as a parameter server, and we send all these updates up to the server. The server is merely going to aggregate these global models and create another robust global model and broadcast it. Now, this goes on for several rounds or several iterations. So at the end of the training, you have one robust global model, which is trained indirectly without directly taking the data through the knowledge of several devices. And you have one strong model created, which can be used by each of these smaller devices to do inference or to do any kind of learning after that. So, for example, if you have a hospital or if you have any medical institutions, they have local, very sensitive and very private data. Now they will get good advantage if they use machine learning, because they can be advanced by machine learning applications in such a way that they can build very good models, etc. So this becomes really important in cases like these. And all these are all backed by data. So the prediction has been that by 2025, we'll probably have about 180 zettabytes of data that would be generated, which means you have mammoth amount of data. So you can call data as a new oil, because using data, you could empower a lot of applications. So especially when it comes to machine learning, we know that any kind of machine learning applications, because we are not extensively giving it instructions of what to do, the more data you feed, the more better it is for your model to be able to train even better and become much better to do your tasks. So we can leverage this, we can take advantage of all this data that is getting generated, probably put it into applications like this and use it for machine learning. But we have to keep it in mind that there are certain data protection laws so that the misuse of any kind of data is avoided and the data are remain private and all the regulations are in place. So we have GDPR set up by Europe, by HFPA, by USA, etc. Now, while keeping these in mind, we can say that in federated learning, we can do some kind of collaborative training, which will address all these data privacy and security problems, and you will have access to heterogeneous data. Also, while keeping in mind that you have restrictions to access, and you will make sure that that is enabled. So this is one of the main advantages why federated learning works that well. Now, the second advantage why maybe federated learning is becoming more popular is the way it is placed in your network. So the traditional cloud computing has very good capabilities. Unfortunately, it is latency driven. It also has a lot of downtime and it is more vulnerable to attacks. So it may be much difficult to use the cloud as is. So that's why another hierarchy was proposed where you add another layer between the cloud and your edge devices, which is called where you put an edge server and you put some base stations between. You basically are making sure that the data is, all the processing is gotten closer to where all the data lives. So the advantage of this is that you don't have much latency, because you don't have to push up all the data all up to the cloud and wait for the processing here. The proximity is much closer, so you have better bandwidth and the resource allocation can be done more efficiently. And this is much faster in real time. So if we can combine this with something that looks much similar to this setup is probably the federated learning, where you can take these data on the edge, enable local training, so you can create local models at the edges, and then probably send up to the updates to the edge server here itself, which creates a global model, and then this process can be continued for several rounds. Then you have a robust model that can be created at the edge probably, which can be used by all the edge devices while taking advantage of both the multi-access edge computing and the federated learning. So I think these two backings to federated learning are most important why they may become very popular is what is the opinion. And however, federated learning also comes with its own challenges. So the first of all, we'll talk about the amount of computations it takes. So here is an example where keeping the accuracy in mind, keeping the performance of your system in mind, several deep neural networks have been proposed over time. And as you see, as time has progressed, accuracy has been increasing, which also means the size of your models are increasing. The amount of operations that it takes internally for computations has increased. So one example over here is if you look at the diameter of these circles over here, it is an indication of how many parameters it has. So the bigger the circle, which means that the bigger is the number of parameters it hosts, that big is the network. So here, for example, BGG19 has about 155 million parameters. So running these things, let's take an example of what it looks like. So if you have to probably take one image of size h by w and you run a filter of size r by s, and you have to do directly one direct convolution of this computations. So one of this computation will result in about hundreds of multiplication and addition operations. So which means that it is very memory intensive. Along with this being memory intensive, it is also not very efficient in terms of the energy, because most of the devices are powered by battery. So it may become very inefficient when it comes to battery consumption. When you have really big systems like servers or data centers, the energy may not be that big of a problem, although eventually in the long run it will be. When you talk about smaller devices like mobile devices, which has already low memory resources, it is kind of constrained in terms of resources and it has limited storage space and memory accesses, then it becomes problematic because the computation will be increasing and it also increases the latency and energy difference. So it can become computationally expensive. The other challenge will be the communication. So let's take an example of probably running a recent 152 deep neural network. It has about 60 million parameters and 152 layers. And let's say we are trying to use ImageNet as a training data set. which is sized about 300 GB and it has 1.6 million images already. So, well, we already know the kind of burden this might put on the computations, on the communication, in a similar way where we see the number of parameters would already have increased for the deep neural networks. We'll see what happens in the training process. So let's have the client devices. So in federated learning, because we first compute the gradient and then we exchange these updates up to the server, as you use a bigger deep neural network, the bigger the update size that is created per round is also keeps increasing, which means that this amount of time, resources, and everything that you need for communicating this update is going to increase a lot. So which means that the communication also can get very expensive. While we have these two things in mind, there is a lot of literature that proposed on making federated learning more communication efficient. Some papers talk about making computation more efficient, and this thing that the communication is not very burdened. We'll see another point of view of this. So we look at all the advances that have happened in the recent years since the time federated learning was proposed until now. So first we'll talk about the local computations. Let's call it working, which means that you're working to make computations. And then wireless communication, where you're talking to the server to send your updates up there. So all the advances that have happened in these few years have been like you have multi-core processors, you have many accelerators that have been proposed. Some active research has happened in the terms of computing hardware. And also in terms of wireless communications, we've seen how rapidly there's been a surge in 5G, and the upcoming 6G also has a lot of research that is backed. So probably because they all target some high-speed communication. So the question is, do we really have this kind of a problem? Are we really constrained on one over the other? So for that, there was a tiny experiment that was conducted where we saw that on a Jetson Xavier GPU, the amount of time it would take for one computation would be about 86 milliseconds. And for communicating this update up through a 5G link of 100 Mbps speed, we saw that it takes about 90 milliseconds. We see that these two values are not very different. So let's see about the energy. Even in terms of energy, when through a similar experiment, we saw that the energy it takes for computation and communications also are not too different from each other when it comes to certain scenarios and when it comes to certain devices. So which means that they can become comparable. So there is no there's no need anymore to put one in front of the other. Instead, our goal has to be to design both computation and communication efficient, where there is balance between the two, and also keeping in mind whether you want energy efficient or delay efficient techniques. I think this has to be the goal. So this becomes the first goal of my dissertation. Second challenge we talk about in federated learning is the heterogeneity. When we say that in federated learning, you can bring any kind of devices of your own, all of them will be collaboratively trained, which means that these devices have different kind of heterogeneity. One can be the system heterogeneity, where the hardware that is bad, the network connectivity they have, or the battery level they have, maybe they are plugged in, maybe they're not plugged in. So the amount of battery they have, all of these, and the data heterogeneity, because the data distributions may not be identical, because the way we collect data from each of these devices may be completely different. They don't necessarily have identical distribution. So the problem these heterogeneity bring in is there can be some weight divergence, and making sure that they all do the training and converge to one global model may be a little challenging, and it can lead to poor performance accuracy. So the second goal of my work would be to design federated learning techniques that addresses this heterogeneity. The third challenge, the final challenge we talk about, is the privacy. Although in federated learning, we do not actively share data and the training data is protected to a great extent, the model updates that you send up to the server can reveal some sensitive information. So for example, in this federated learning process that we have, though we are only sending the updates up to the central server, let's say there's an adversary who can intercept these updates and takes these updates. We'll see what they can do with it. So one example is they can perform some kind of a gradient inversion or a model inversion attack, where with an access to the output, an adversary with some access to some machine learning system, for example, machine learning as a service, or some other model like this, having access to it, they can do some kind of reverse engineering attacks on this and try to recreate the data. So the training data, for example, has this person, as we can see, this can be almost reproduced, and which is almost identical to the training data, and it is already almost reproduced. Another attack would probably be a membership inference attack, where using some kind of similar attack technologies. The adversary can check whether this particular person is present in the data set or not, in the training data set or not. So these problems can happen with just sharing the model updates as well. So the third goal would be to design privacy-preserving federated learning techniques that tries to address this. Hence, the goal and contributions of my PhD are as follows. I try to target efficiency, privacy, and personalization while trying to make federated learning more mobile device friendly. So when we talk about mobile device friendly, which means that you have smaller devices, which have more compact computing and communication capabilities underneath it. And all these would be the requirements that we need. And because it is mobile, which means that it can be carried around, that is the reason why it is made so lightweight. So we should try to target applications which can be run on it more efficiently. So to target the heterogeneity problem, we try to make some personalization of the algorithm. So for that, I propose two of my works. And for the privacy concern, I'll talk about some sketching, quantization inspired work. And for targeting the efficiency, there are a couple of works which talk about energy efficiency and one about delay efficiency. In either cases, we try to balance the overhead of both computations and communications, so that there are two of my works. I propose to do this. So overall, I'll talk about three of my primary works alone in today's presentation. Talking about the first work, it's titled towards energy efficient federated learning, federated knowledge transfer over heterogeneous mobile devices. The main motivation of this work is to make sure that any large size deep neural networks make sure that we have good model accuracy. But unfortunately, the downside of this is that you're training on resource constrained devices, which means that the energy consumption would be very high and it could be very battery draining. Some of the related works that talk about dealing with these problems is one is probably the federated averaging, which tries to make it more communication efficient. But unfortunately, if you have very large deep neural networks that you're trying to run, then increasing the computations just because you want to decrease the communication may become a little expensive in terms of computation. And the other set of work is probably the area of split learning, which tries to reduce this problem of computations where you take a big neural network and try to split it into two parts, and you put the bigger chunk of computations onto the server and the smaller one on the client, and make sure that this kind of training happens like this. But unfortunately, because for every round of your mini batch iteration, like the forward propagation, back propagation, you have to keep communicating to and through the server, it leads to some severe structure problem, and also the communication becomes really expensive. Instead of so we want to make sure that we try to propose a work that does not bring these kind of overheads as is. So for that, I use the knowledge distillation or the classic. For that, I'll give you some preliminary about the classic teacher-student approach. So knowledge distillation is where you're trying to transfer the knowledge from a big model to a small model without trying to lose the validity. So the big model's advantage is that they have higher knowledge capacity. Unfortunately, they're computationally expensive, whereas smaller models have smaller learning capacity, but they're computationally less expensive. So we can treat this bigger model as the teacher and the smaller model as a student, and we'll see how we can try to leverage distant knowledge from one to another. So for that, we use this classic student-teacher approach where the teacher is usually pre-trained and we have the soft label instead of the hard labels. And after that, the student tries to do the training using the same inputs, and he tries to come up with two kind of outputs, one from the softmax, which is the soft predictions, and the other is a hard prediction, which he can compare against the ground truth. So using the first one, we try to use a distillation loss where the student is trying to constantly compare with the teacher's outputs and try to minimize this distillation loss. And in the second part, because you want to increase the accuracy of prediction, the student tries to compare against his own hard labels that he has in the data set and tries to come up with a cross entropy loss. And a combination of these two things is the overall loss, which the student will try to minimize in order to become as efficient as teacher in terms of predictions. But unfortunately, the problem by using this approach is that the teacher has to be pre-trained and they have to have similar or data usually, and this usually happens offline. So we try to take a different take to this. So we try to imagine this probably a classroom full of students, each of whom is good at their own topics, their own subjects. And there's a teacher who has higher learning capacity. So here, without the student talking to each other or sharing knowledge with each other, but they only talk to the teacher, and the teacher will make sure that she creates probably a lesson plan or chapters in such a way that the whole class is probably enabled with knowledge learning from of each other at the end of the day. So here we can see the students who have private and different information, and teacher has access to all the knowledge. And here we can try to enable mutual learning and also make sure that the student's personalized goals are met. So if the student probably is stronger in one topic over the other, they can finally fine-tune their own learning in terms to make their model more robust. So this in terms of federated learning can look like this. These students can be treated as clients who have non-IID private data. The server probably is like the teacher who has access to everyone's knowledge. So our approach would be something like this. On the teacher, we try to run a big model, and on the student, we try to run a smaller model like probably Resonate 8, and we try to distill knowledge between the two by using this kind of algorithm. But first we share the pre-share the labels with the server. We do not share the data though. And the student does the local training by himself, just like how we do it in federated learning. But instead of sending the model updates, we are sending the intermediate results of feature maps and the logics to the server. The server will take these, aggregate the logics, and try to do the training of his own. He does not have any data, but he only has the labels. He tries to do the training on his own and then sends the logics back. And this way, this knowledge can be enabled between the two. So majorly what we're trying to do is we're shifting all the major computation burden towards the teacher or towards the server. So we can enable some kind of bi-directional learning. The teacher and student are learning at the same time. And we are not sharing any data. And this also happens online. So if there's any changes that happens in the network, right, then we have more participants or we have another server, etc. All of these can be taken care as is because the whole thing is dynamic. And also this can be more energy efficient as we see in the future. So how does heterogeneity play a picture here? We are trying to use Wasserstein laws, which will try to reduce the difference between the logics here. And we use the cross-entropy laws to make sure that the accuracy of the models are much high. We have one of the student, one of the teacher, because both of them are doing training. So overall, the student and the teacher will have their own objective functions in this way, and they're trying to minimize this loss. And in lieu of energy consumption, we said the overall energy consumption here is a combination of the local computation energy and the wireless communication energy, which can both be defined as follows, which have their own dependent parameters on the frequency and voltage. Here it is dependent on the number of bits that is power transmitted, and the transmission rate that you have, what is the resource blocks that you allocated, etc. So in combination, the overall energy consumption can be given in this fashion. So, and then we also want to make sure that the system is not losing out on the model efficiency, like in terms of learning performance is not lost because we're targeting efficiency. So we try to introduce an accuracy metric called the accuracy aggregate metric. So when we try to do some optimizations, instead of measuring the server's accuracy, what we're trying to do is we take the students' heterogeneous data of what they're running on, take that accuracy, and we try to do some kind of an aggregate here. And we use this metric to see that it's much simpler to use. And we try to balance the computations and communication energy because as we see, there is not too much difference between the two. So our goal is to make sure that we target learning plus energy efficiency while balancing the computation communication and making sure that the devices have data and system heterogeneity, and they should also be taken care of. So we try to formulate the problem in such a way that we try to find a solution of finding the basic block with respect to time and accuracy and bandwidth allocation in this fashion. So we're trying to minimize the energy while taking care of communication parameters of resource blocks. And for computations, we're trying to set a deadline for the every round. And then to make sure that the learning accuracy is still met. Otherwise, in terms of energy accuracy, all the parameters will be chosen probably to their minimum. We want to avoid the problem. So we try to set some kind of a threshold for the accuracy that you want to be met. And then for the knowledge distillation parameter, we use this basic blocks. Basic blocks is nothing but one of the chunks of your neural networks where you say the number of, you have so minimum required model layers to work. For example, you have like probably 2 convolutional layers, you have 1 fully connected layer, you have 1 input layer. All of that was called as a basic block. So we want to make sure that you don't want to make the client so small that it doesn't work at all. So you're trying to set some constraint on that. So that is why we are using this constraint over here. So this problem is a mixed integer non-linear problem. So we are using a heuristic approach to solve this empirically, and we are able to come up with values for these. So then we did the performance evaluation of this. For that, we used the Cypher-10 dataset. And for the baseline methods, we used the Federated averaging and split learning that I introduced in the previous slide. And we are using ResNet 56 and ResNet 110 bigger models on the server. And for the client, we're using the smaller model like ResNet 8. And most of it, we're doing simulations on an NVIDIA server, Linux server. But for the energy experiments, only the measurement, I'm trying to use a hardware prototype of Jetson TX2. And I try to do the energy measurements of the clients on that. And in terms of performance, to see the convergence of this model, first we'll check on the homogeneous data when they have IID. We see that the training loss is much lesser, and also the accuracy is much faster, higher. The pink one is ours, which is called effect. We see that ours is much better than the baselines. And especially when it comes to non-IID data or heterogeneous data, we see that the performance of the actual baseline methods are much lower, but our method works much higher, it works much better, whether it comes to training loss or accuracy. So we see that our promise of heterogeneity is maintained over here. And in terms of energy efficiency, we see that again, we see on IID data, our energy usage is much less. And in terms of non-IID data, we see a lot more difference between the baseline methods and our method, and ours works even nice with heterogeneous data. So basically our argument that you're shifting most of the training on the powerful server. Because of that, the energy conservation on the mobile devices is maintained. And in terms of computation cost, we first try to see the number of parameters these houses, because of that you can see the memory accesses. So because we're using just a small model like a ResNet 8 or 4, ResNet 6 or ResNet 10 example, for example, the number of parameters it houses is much less, which means the computations is much smaller compared to the baseline methods. And in terms of computation time, we were trying to measure that how much time it takes per mini batch. And our method is very less compared to the baseline methods again. So we see that we have less computations. And in terms of communication cost, try to come up with a metric which measures the size of all the hidden vectors and logics that you're sharing across the rounds. And in terms of that, we see that our effect has lower computation cost because we have fewer exchanges in compared to split learning, because it has to do more frequent communication. So the takeaway of this work would be that we proposed an algorithm called effect, which has mutual or bidirectional learning, which uses knowledge distillation. And the teacher is continuously guiding the student in terms of learning. And we are targeting the goals that we wanted to, because we're using Wasserstein laws, which supports any kind of heterogeneous data, and we're doing knowledge transfer instead of doing the aggregation. So even if you have a heterogeneous system, no matter what kind of system hardware that they have internally, it does not really matter a lot to us. Our accuracy can still be met because of this. And at the end, because we have individual models plus a global model that is created, we can just fine tune the models on the local devices to make sure personalization is met. And for privacy, we don't actively target privacy in this paper, but we can say that instead of using model updates, we are just using feature map vectors because they're not very well formed. The privacy is much better than federated learning alone. And we saw the performance accuracy was good, and then the energy consumption was also even better. Next, I'll introduce my second work, which is titled SQUAFFLE, Sketch Quantization Inspired Communication and Privacy Enhanced Federated Learning. In this, the challenges that we try to target is the efficiency and privacy part. Mainly, we talk about how large-scale distributed training is usually limited by the network bandwidth that you have. So, and the other thing is the privacy. So both of these problems are individually targeted in most of the papers. Like we see model compression papers targeting this, and we see some privacy papers trying to target the privacy. And in our work, we'll see if we can put these two together and make it work. So for that, we use something called as count sketches. So count sketches comes from the streaming or natural language processing, where you try to take the frequency of the very commonly used words and try to make a model out of it. Here, let's say you have several colored balls and you're trying to count the frequency of these balls. What we try to do is we take these and try to put them in a table, all these coordinate updates. But before putting them on a table, directly projecting them, we try to use some kind of signed hashes, and then we try to use some bucket hash functions. All of these values, only the person who's doing this would know, nobody else would know. And then we project this into another dimension in this fashion. So if somebody has to retrieve these values, they cannot do it unless they know these sign functions and what were the keys that were used to do this kind of hashing. So, and even that, it is really simple that you can just take the median of it and you can know what was the actual update. You do not have to do much work over here. So we use this in federated learning. So why does this become important in federated learning? Yes, it has many characteristics, one of which is mergeability. So in federated learning, because we just do this kind of aggregation, it is really easy. You can just take the sketch updates and do the same thing. And it is more communication efficient because at the end of the day, you're trying to project it to another dimension, which means that you're doing some kind of compression. So the uplink bandwidth problems that you have can be taken care of this. And the main property it has is the privacy. Because you're using some kind of independent hash functions, you're concealing the identities of the user. So even if this model update has actually gotten into wrong hands tomorrow, unless they have their hash indexes and seeds, they will not be able to retrieve this, not even the server himself. So even if you want to run a query and try to get the gradients, like how we do in the model inversion attack, it will be much difficult to do it with this. And also this exhibits some strong differential privacy properties. So with Sketch in this paper, I'm trying to use quantization because quantization, as we know, is a very mature technology which tries to reduce the precision of your updates. So because of that, you have large computational gains. And in this paper, I'm trying to use stochastic quantization. And because that, I'm trying to propose a mixed compressor called the SQUAFFLE. And for that, I'm trying to write a lemma to show that even if you use a quantized sketch update, you'll still be, which has this particular size, you can still be able to retrieve the original values by using the median value, just like we showed in the last slide. And using that, how we fit this into the federated learning framework is in this fashion. We have the global objective similar to federated learning, where you're trying to minimize the loss, which is actually an aggregate over the local losses, which is written in this way. And the key steps of this algorithm would be this. The server would initially initialize or aggregate your sketches and send broadcast this to the local models. The clients will first perform the query to using the median value to get the original value. And then using that, after extracting the global update, it will try to run a local training. After that, it will sketch and quantize this and send it up to the server. This process can be repeated until convergence. So what is the differential privacy property we were talking about is this. A small preliminary about differential privacy is that, let's say you're running a randomized algorithm on one of your data. Here, probably you're trying to getting the outcomes of your random coin flip. And you have one here, and the other in the other experiment, you're trying to take out one person out of this data. And we see what happens. We see that the output is not much different between the two. And that is the whole requirement of differential privacy. So whether a participant is present in your data set or they are not, the output of this should not tell you that this person is not present or not. So that way, many of the membership inference attacks that we were talking about in the beginning will be avoided. So, and this difference is usually bounded by a ratio called epsilon, which is the crux of your differential privacy definition as given over here. And one of these papers showed that the count sketches actually display some epsilon differential privacy properties. So which is really useful for us. And using which we do some theoretical analysis of our mixed compressor in this slide. First, we show the convergence of squaffle over non-convex and strongly convex objectives. For that, we use two assumptions, which are very standard in federated learning of smoothness and bounded variances, etc. And we show the convergence. And from this, we can infer that there is actually some kind of speed up that our algorithm provides. And in terms of the compression, because we're doing quantization and sketches, both of them are compressions in their own way. If you use more participants, we can show that you can scale down the amount of noise that you're doing, so we can still learn collaboratively. In terms of privacy, what happens is if you create a hash table size which is too large, which means that the amount of compression that you're producing is less. So if the noise is not too much, then it means that you have to expend a lot of more privacy budget on your own to add the extra noise to show the privacy. So that will weaken the differential privacy, right? So there is a careful trade-off between the privacy and utility that you'll have to take care of. So along with this theorem, some certain corollaries and side results that we obtain tries to show what is the amount of communication rounds that you will need. That we show that compared to the state-of-the-art results that are available today, our algorithm shows some kind of speed up in terms of the efficiency too. And in terms of the performance evaluation, we show that compression and performance both can be taken care here. So we are measuring against FedSGD, which is a popular gradient update on each round that it provides. It is a very popular federated learning algorithm. And in terms of compression, we show two things. In quantization, we try to change the bit size to 4, 8, 16, etc. And in terms of the sketch size, we try to change the rows and columns of the table in this way. So if you have very smaller values, which means you have a very small hash table, which means that you're very tightly trying to compress the whole model. So in terms of accuracy and performance, learning performance, we see that we are even by doing this kind of compression, our learning performance is not lost. And in terms of the communication efficiency, we see that the more you try to do the compression, it takes lesser time to finish your training. Unfortunately, there is a small hit in terms of accuracy if you compress a lot. So there's a careful trade-off between your amount of time it takes making it communication efficient versus the accuracy. And there's this careful balance that you need to take care of. So the takeaway messages from this work is as follows, that we used quantization and count sketches to make sure that we do communication efficiency and privacy preserving. And we also showed some theoretical results for convergence, and we showed how differential privacy properties was leveraged to show the privacy enhancements using our compressor. And the overall analysis was how we can control the size of the hash table and try to balance some kind of trade-off. And then finally, I will introduce my third work in a very brief way, which is titled IoT Device Friendly and Communication Efficient Federated Learning via Joint Model Pruning and Quantization. I call it GOEP. And here, we are trying to solve the challenge of how really big size neural networks, which have much good learning performance, can be run on smaller devices, which are memory limited and are resource constrained. And also the frequent exchange of model updates, which are bigger in size, usually create a communication bottleneck. We're trying to target these problems using GOEP. We're using weight and coordinating quantization in conjunction with model pruning. And we also make sure that some errors that were created probably during the compression was all taken care of by using some error feedback. And the main objective remains very same as the usual federated learning, where the global objective is probably to trying to minimize the loss average over the devices, and where the local loss function can be defined as in this fashion, where this xi is your local meaning batch distribution and p is your local distribution, data distribution. And here is how the algorithm works, right? So in the first round, the server initializes the global model, which is broadcasted, and all the users download this. And first they do pruning. For pruning, we're using the saliency-based pruning, which means that the connections which are not important, the weights which are not contributing much, are all set to 0. So after that, we try to do the local training of the devices, after which we try to see if there's any error feedback that we need to apply. And then we do a gradient quantization so that we can make sure that the computations is reduced. And here we're doing model pruning because we want to shrink the size of your neural network. And after this, we send the updates up to the server. The server does the aggregation and tries to do some kind of weight quantization before sending it downstream. So this is how it works. So we did some kind of a convergence analysis of this by having two assumptions about the elections continuous. And then we also use some kind of Togon traction property for compressors. And then we came up with the convergence rate of the algorithm, where we see that our algorithm converges to a point that is up to a constant that is related to the amount of compression that you provide. And here this C is basically dependent on how well you started and how the loss minimizer that you have. And all the other parameters that are here are mainly dependent on the compression levels. So basically, if you have higher values of gradient and weight compression, gradient quantization, like if you have 8 bits or 16 bits versus having 4 bits, for example, which means that you have lesser error. So the higher precision that you give, which means the lesser error you have. And similar observation is with tuning. If you prune a lot, which means that if your compression is a lot, which means that you're creating a lot more errors in the system, and probably the system is probably more biased. So there is a trade-off again between how much you want to compress and what is the learning accuracy that you want. If you want to target a lot of efficiency, then maybe you want to compress more aggressively. Versus learning, if you want to probably have much more accurate models, you will probably want to tone down the compression a little bit to make sure that you have a balance between the two. And in terms of performance evaluation, we used ResNet 20 model with Cypher 10 and LeanNet 5 model with MNIST, all image data sets. For the metrics, we used performance accuracy, which is nothing but the number of product predictions by total number of predictions to see how accurate the system is. For total loss, because total time, because this is not an actual experiment where we're trying to do simulations, the way I calculated overall time was the amount of time it took for the training to complete. And for convergence, we're trying to measure the training loss. And for communication efficiency, I'm trying to see what is the number of communication rounds that were taken. And for the baselines, I'm using Federated averaging and one of the pruning papers and one of the very popular quantization paper. And we see that for the communication efficiency, after presetting some kind of accuracy like this for MNIST and this for Cypher, we see that the number of communication rounds we take, the one that marked in pink or purple is GOEP, which is ours. Ours takes the least number of communication rounds, but also the test accuracy that we have is much higher than others. So we know that our system is more communication efficient. And in terms of convergence and accuracy, we try to change the number of quantization bits. We try to change the number of pruning, level of pruning that we have. If you do 0.9, which means that it is a very aggressively pruned network of 90% pruning and 8-bit quantization. So like this, we see that no matter how much we change, we are still able to converge. And our main method has much faster conversions. And yeah, this was in terms of the ResNet and LeanNet 5. We see that ours work much better. These were all for IID. We also try to replicate the same result on non-IID data for heterogeneity. And we saw that even for heterogeneous data, our algorithm actually works much nicer compared to the other algorithms. And in terms of evaluation of time, we are trying to set the number of communication rounds in advance, and then we'll complete the training to see what was the accuracy that was made, that was attained, and what was the time that it took. We see that our accuracy attainment is much higher. You can see that advantage, especially when it comes to a more complex neural network like ResNet compared to LeanNet, and also when it comes to more complicated, complex data set that you underline that you use. And we see that in either of the cases, the amount of time that we take to complete the overall training is much smaller compared to the baselines. So the takeaway messages of this work is like this. We excuse me, we did a threefold compression of joint model training and quantization, and showed theoretically how we were able to show that this has a convergence, and it can, and also in the paper we show that this can be extended to any biased and unbiased compression schemes. Both theoretically and through experiments, we've shown that you don't necessarily have to stick to using stochastic quantization or deterministic quantization. You can use one method over the other. You can even use sparsification we show that any of those methods can still be fit into this algorithm and this algorithm will still work. And in terms of performance, we showed how we reduced the overall training time, the number of communication rounds, etc. And we also saw the model compression ratio impact that we had on the performance. So overall, the conclusion for today's talk was this, that I introduced 3 of my main works. Firstly, GWEP, which included a 3-fold compression strategy. And I tried to talk about effect, which does energy efficient better knowledge transfer. This targets the heterogeneity problem and also makes it more personalized. And Squaffle tries to target the efficiency and privacy. Overall, we are trying to make way for mobile devices to participate in the federated learning process in such a way that we're making efficient, private and personalized designs. So now I'll talk about a couple of my works. One is ongoing. The ongoing work here I'm trying to target is called adaptive learning, local training. It's called adult. So the argument here is that when you have cross-domain heterogeneous data, and you want to make them all into come up to one model and do the training, and you want to have one single feature extractor, or you want to have one single model, which means that the accuracy may not be that great. But if you think about having them together, like probably have a global model and probably in conjunction try to use local models for fine-tuning in such a way that you can try to target both the problems, then we see that it works much better. So the crux of the algorithm is like this, that let's say the training progresses through global rounds in this fashion, from left to right, which means that initial rounds of your training, you see that you need more of the global models than you need dependence on the local models, because you want to create more client agnostic models in the beginning of the training. But as training progresses, we see that our user devices, especially based on their heterogeneity, based on that how quick they are to learn, they probably will learn faster, which means that they don't need the global model that much anymore. Even the global model does not need your contribution that much. So as training progresses, we try to make it more client specific by reducing the dependence on the global model, but using more of the local model to the training, so that at the end of the day, you have one robust global model and you also have personalized models. You don't have to separately go out and fine tune models, but this will already be taken care of. This is what I'm working on currently. And one of my other future works is the multi-job federated learning, where especially when you have slow devices, stragglers, they'll take probably all the amount of time to perform one task, but other devices maybe are faster. So you can give it more number of tasks to do in the same time. So for this, we use some kind of a scheduler on the server and make some asynchronous training and make sure that you try to do this kind of a scheduling while making sure that you are not creating any bias by probably selecting the faster device all the time. You're trying to ensure fairness of participation. And this is my future work. And here is my list of publications. The first of which are, the first one is on review and the second one we are trying to submit and it is ready for submission. And thank you. And here is actually a list of inventions that I had when I was trying to do some internship in the industry last summer. And that's all I have. Thank you so much. Free to answer any questions if you have.
Okay. Dr. Pan, wake up.
Yeah, I'm here. Wake up. I'm still awake.
Okay, so
yeah, I take a nap during the presentation. So
yeah, we can hear the snoring, even you muted.
Okay, so any question from the committee members?
Yeah, Hin, you go first.
Yeah, so it's a very nice presentation, and you talked about, large language model at the beginning. I mean, it doesn't plan to investigate federated learning in the context of large language model? What do you think about that? I mean, what applications can you facilitate?
Okay, so Dr. Ven, the reason I was talking about that is thinking of my ongoing work. There I'm trying to use some kind of natural language processing, like I'm trying to use a Shakespeare dataset and also some Twitter dataset to make sure that when you have really frequently occurring messages and you have really long messages, how we can be able to train those models. And because the generative AI is so popular these days, I think that these works can use those. And also, I was also in the process of trying to run all my old code on some large language models. But I was not able to finish it before today's defense. But that was also something that I was attempting, because I felt that earlier when I proposed those algorithms that were mostly on image datasets, because it was much harder to target image datasets those days. So I was also trying to see how I can fit them all into large language models. That's why in the introduction I talked about those.
So could you clarify, what do you plan to do with the large language model that you run and you couldn't finish?
So all I was trying to do with the old algorithms was to run them on large data sets from probably Twitter and probably the Shakespeare data set, because these have the large news, several of your news that keep coming on your feed. And you probably want to create a global model which can extract these and try to, again, we can try to target use the compression to target the efficiency of your models and also be able to make them more accurate.
Yeah, I'm curious, like if there's any sexist application of like federated learning to GPT or large language model, we can demo. It would be very interesting.
Right. Yes, exactly. So when I was doing my current work with personalized federated learning, that's literally what I was thinking, that maybe I should like go back and try to remodel these, or probably try to tune them in such a way that I can accommodate these models as well.
But first,
So
I mean,
can have those.
we should think about what application do we want to facilitate. I mean,
Okay.
I don't think we can train large language model from scratch like GPT.
Yes.
So I tend to leave the training to big companies. And let's say we get the big models from Meta, right? Meta has released their large language model, make it public. We get that. What do we do with this? If we have federated learning and large language model, what do we do to maybe facilitate the adaptation of this model to a new task, for example? You know, I wouldn't say we should train from scratch, but at least we can refine several parameters in the model, you know, and we have in my lab, we have a work in which we have foundation model, and then we refine it using prompting or a few minimal weight tuning within the network to make it work really well for a new application. So perhaps, you know, in that case, you can showcase, here is a federated learning that we can combine the data from multiple users, multiple sources, and then we have a central foundation models that will, you know, be the backbone, you know, and then we show that we can adapt using federated learning with the foundation model. That's gonna be a very nice paper, I think.
Yeah, yes, I think it's going to be really interesting, Dr. Vin. Yeah, I think we should do that. Getting data from several sources.
Yeah.
And yeah. That's it.
So Mel, I mean, what do you think about it? I mean, if you're interested, we can explore some direction like this. So in foundation models, means that the models trained by big companies like Meta or OpenAI, I don't think we have the ability to train that. It costs a lot of money. Every time you train, it's cost $1 or $100 million model. But what we can do is we can adapt, right? Adapt these models to
Sure.
new data sets, new scenarios, and you know, we can use federated learning for adaptation, you know, and showcases.
Sure.
Okay.
I'm very interested in that. But you know, Pavana is graduating, so I need to find a proper student to work on that.
Okay, yeah. No, I mean, my student can also do that. If, you know, you guys provide some advice or guidance, we can also do that.
Sure. We can definitely collaborate on that in the future. Yeah.
Yeah.
So the second question I have, Pavana, is are you aware, you know, this federated learning work for multimodal data, where people apply to more than one modality, more than just image, but maybe there are 2, 3 modalities, and then maybe some site will have missing data. How do you handle them?
Especially when it comes to the using technologies like the knowledge transfer rather than completely federated learning, I think it'll be easier for us because let's say that some of the models have very different data, or some of the models do not have sufficient amount of data, or they do not have sufficient amount of labels. Because we try to leverage the knowledge distillation, we can still be able to use some kind of a teacher-student model and try to extract information from the teacher. And this way we'll be able to train these students as well. And when it comes to different modalities of data that probably the participants will have, again, we can use the same thing. And because we don't have to stick to just using the federated averaging all the time. We can use some kind of a distillation and different kinds of loss functions, like I was talking about in one of my works. I think that way we can be able to accommodate these kind of participants as well and be able to build a federated model.
No, I mean, what I mean is that it doesn't need work handling multi-model data. The reason I mention is because of the following. In multi-model data, you might have, image with a lot of, with a lot of parameters in the network responsible for processing image. So the gradient will be mainly, all the parameters will be mainly focusing on image, and while you have clinical data or vector, there are very few, maybe there are very few parameters responsible for processing them. So the gradient may become heterogeneous, right? There's anything fundamental that we need to take care in these cases.
Okay, so I think in terms of these multi-model data, things that you will have to keep in mind would be what probably is a heterogeneity that you're bringing in. Because if they probably cannot participate in the training as much, which probably would mean that you can try to do a selection of the models in terms of training every round. You can probably use a subset of models in different rounds, so that in every round you're trying to pick models. You're trying to pick participants in such a way that you're trying to cover different type of dimensionalities and different kind of participants, like people who do not have much data, who cannot contribute much to the gradient, we use them. And in another round, we can probably try to introduce other set of them. So when you're trying to aggregate them, we can still put them together. So if the gradient direction is going in the other way than we want, I think in this way, we can make sure that we do more training when you do this participant selection. And then that way we can still be able to achieve the results that we need.
I think in the literature nowadays, in the recent 2 years, there are many papers that talk about the multimodality fusion, right? So probably we can refer to that. But I'm not sure if you're talking about different story, Hannah. It's mainly, yeah.
It's the same story. I think I look briefly on, so I see some work on multimodal federated learning, and I think that one of the challenge is what I mentioned here is modality discrepancy. If you think a network and you feed multiple data modality into it, the gradient might not be of the same in the same scale or dynamic range or distribution, right? And then how do we handle that in the process of on the process of Pavana have developed, in terms of how to manage the gradients? Does it converge? Does it guarantee the convergence still? If you have different modalities, different gradient magnitudes and things like that, will it? I mean, maybe theoretically, but practically, maybe it will diverge. I mean, we have problem with multimodal because, you can imagine some modality can be text, some modality could be genetic sequence. They're very different. And I'm just wondering, during that process of federated learning, how do you make sure that you propagate the gradient in the optimal way with different types of gradient for image, for genetic information, and so on?
Yeah, go ahead, Pavana. No, go ahead.
Okay, I have one other take on the same, Dr. Min, like two things that I would want to say. One is because of probably this problem, some of the works are trying to share some intermediate results with the server when we try to do the training, because of the same problem that probably the gradients are probably in different directions. So instead, if you take some feature vectors, take it at that level and try to build the knowledge in the initially, so that the deviation can be reduced a little bit, and then you can continue with the training. And probably the second way, probably in the perspective of related Okay, let me talk about my own work. In terms of probably one of my own works, I'm trying to, because I'm thinking that I have very different data. I do not mention it as multimodal, but I'm just saying that the data is very non-identical amongst the devices. So I'll share the logits and feature vectors instead. So we can use that to probably do some more training. It may take a little more time compared to when you have identical data. But this way we'll be able to reduce this kind of a deviation with the gradient and still be able to do the training. That would be one perspective. The other related literature that I'm saving these days with in terms of whatever exactly that you said using multimodal data was, I think some of the recent Google works are trying to use some kind of partial learning where they're not discarding the local models altogether. What they're trying to do is they're using a combination of the global model and they're trying to initialize certain parts of their local model in training. So every device will bring whatever is the biggest deviation that they have. So they keep measuring the deviation in every round and they try to add that to the global model and then send it to the server. So now the server doesn't have just the global model part. He also has what is the deviation that every client has. And then they'll try to increase the number of rounds and try to minimize this difference. So eventually, I think you will be able to solve the problem that you are saying about the gradient deviation.
Okay, thank you. So last question for me. You know, nowadays model is very big. The foundation model is very big. And it's at the moment, it's hard to fit these models into mobile devices. So what would be a good strategy if I want to fine-tune foundation models used with mobile device in the loop?
So yeah, that's a very good question. So I think for that, you can first try to see if we can try to reduce the model size if we can. So I think compression is going to be a very efficient strategy to do that. And because you want to make sure that the learning performance of the large models is still maintained, we can try to use some of the strategies that some of the papers that I have proposed, or probably the ones that are in the literature about using any kind of model compression. So you can try to reduce the computations in terms of probably you reduce the precision of the bits that you're using. Maybe you can use some quantization, or to reduce the overall size of your model. We can try to use more different strategies of pruning. Like, for example, I'm using an unstructured pruning. Maybe you can try to reduce the model channels. You can try to change the size of your filters. So we can try to do some structured pruning like that also to make sure that the sizes are reducing, but still the accuracy is not completely lost. So I think in this way, we can try to take any big model and try to put them in compact devices like mobile devices. We can still be able to achieve good task.
Do you say that we should reduce the model, you make it smaller and then do pruning?
Yes, we can try.
But sometimes I don't want that, right? So I can have, what I can live with is that I can have a central server, the original model. I like to work with the original models. I list the server, and then you can have the smaller model in the mobile device, but I still want the quality of fine tuning on the big model. I mean, there's a way to let the mobile device use a smaller part or a subset of it, and then have the central server to deal with the original model.
Yeah, yes, Dr. Ben, absolutely. Yes, Dr. Ben.
Yeah, probably you can answer the question from the, remember the paper subnetwork?
Yes.
And also to deal with the device heterogeneity.
Yes.
Yeah, probably you can address this question from that perspective.
Yes, Dr. Ben, absolutely. So Dr. Ben, I would say two approaches that we can have. One is what Dr. Pan was suggesting, that in recent times, what we're trying to do is we're trying to do some kind of a sub-model extraction. So you have a big model, and we try to take the sub-model out of it and try to put those on smaller devices and try to get them working. So one can be split learning that I was talking about, but they come with their own disadvantages. So instead of that, we can use some other newer aspects of trying to you will try to see what is the deviance that you have between the big model and small model, and you try to keep extracting smaller models out of these and try to do the training. I think one is that it's called a small model training, sub-model training, that is just picking up now. And the second would be in the perspective of my own work that I've proposed recently. I would say the federated knowledge transfer would be an excellent algorithm to use in a scenario like yours, where you do not want to touch or alter much of your big model that is available, or we can even try to change it a little bit in a way that you can pre-train and set it and fix it in a central server. You call it the teacher and just leave it there. And in terms of the smaller devices that you have, you can try to do the knowledge distillation in terms of the federated knowledge transfer. Just get the knowledge of it and train smaller models on this. So either we can do this federated knowledge transfer, where the accuracy is not affected, the model in the central server is not affected, but still you're getting smaller compact devices which have good learning performance, or we can do the submodel extraction. But that will require a little more knowledge of how you extract and things. But yeah, 2 ways to do it.
Okay.
Yeah, allow me to add something, right?
Yes.
First of all, from inference perspective, there are many works. Probably you can check Professor Song Han at MIT. He did a lot of work to do the pruning, to do the model compression, whatever, to make it happen in terms of inference on mobile devices. Also do some operating system stuff. But from training perspective, although Pavana mentioned many things from, I think from theoretical perspective, but from practical system perspective, I don't think, for example, model compression, right? So model quantization, I don't think current chips, they can support model compression. Model quantization. For example, NVIDIA only severe support from 32 bits to 16 bits, right? For smartphones, I don't think so. I don't think they support model quantization. For pruning, still, I don't think so. I don't think current chips and hardware can support that. So people only can verify that on FPGA, but in the real mobile system, currently, we can only train very small model. For example, 2 layers in, at MINIST, this kind of data set, we still cannot train big models. That's the current status, but I don't know in the future, probably with the advance of hardware and other things, potentially we can do, more complex training. But for currently, I don't think so. Yeah.
Okay, thank you. Thank you.
Thank you.
Thank you.
Yeah, I think I don't have much question because I have heard this multiple times. And just a quick question: where will you go after graduation?
I found an industry job, Dr. Han. I got a research scientist position at the HP Labs.
Okay, that's
So-
congratulations. Yeah. So
Thank
you're
you. I'm
still,
going to
so you're
California.
still here, California. Okay.
California.
Yeah,
Yes.
yeah. Many people in California. Yeah. Okay.
Yeah, we have a lot of alumni. Yeah, big group alumni, many of them.
Yeah, the same. I think that when the economy is good, okay, they all go to the East Coast or West Coast. When the economy is bad, they all become oil company here. So the pattern is very interesting. But that's good. So that means no matter how, okay, our student can find a job.
Yeah.
Yeah.
Pavana will become a millionaire very
Yeah.
soon.
Pavana, remember that, okay? Yeah, during the last 5 years, okay, I treat you better than Dr. Pan.
You did. Yes,
You
definitely.
still
I'll
need
never
to
forget
find
that.
our lab, find my lab first. After that is Dr. Han's lab, Dr. Wen's lab.
Yes, definitely.
Okay, I'm just joking. Okay.
Yeah.
Okay, so maybe we have to kick
Yeah.
into the
I just have to say one thing.
In that case,
Yeah.
can you move the host to me back again, so
Yeah.
I can put you in the waiting room? Okay.
Sure. I'll pause the recording, or should I just stop the recording?
Stop recording, please.
Okay.
Yeah.